Hello everyone and welcome back to EET1011. Today's lecture is going to be on chapter 6, series and parallel circuits. As you may recall, in chapter 4 and chapter 5 we did cover series circuits and parallel circuits respectively. This chapter, chapter 6, covers a combination of chapter 4 and chapter 5, which is series and parallel circuits combined on the same circuitry. The topics that we're going to cover in this chapter will be finding the total resistance of a series parallel resistance. In other words, when we have a circuit that contains resistors in parallel and resistors in series, we are going to find the total resistance for the circuit. We're also going to analyze the resistance strings in parallel and resistance banks in series. So recall from chapter 4 that a resisting string is basically resistors that are in series. However, we can have several strings that are connected in parallel. And also when we have resistors in parallel, these are called banks, but we can also have several banks in series. So we're going to analyze and determine what's the total resistance for this type of circuits. In section 6.4, we're going to work with resistance banks and strings in series and parallel, a combination of all of these items, the strings and the banks connected in series and parallel. We will also analyze series parallel circuits with random unknowns. That means, sometimes we will not know the values of certain components on the circuits, and we are going to discover and apply techniques that help us to determine those values. Section 6.6, we will talk about a special circuit called the Wheatstone bridge, and at the end of the chapter we're going to troubleshoot some open circuits and short circuits when we have parallel and series circuits combined. All right, let's get started with an overview of series and parallel circuits. A series parallel circuit or combination circuit combines both series and parallel connections. As you might recall from chapter 4, we only talk about series, and then chapter 5 we talk about parallel connections. So a series parallel circuit is a combination of these two things. And these type of circuits are very common in electronics. Series components form a series string, and parallel components form a parallel bank. Like we talk about when we talk about series strings in chapter 4. If you have components connected in series, so they form a series string, and when they're connected in parallel, this connection is a bank, a parallel bank. Okay, let's see an example. Okay, on this circuit right here, we have a voltage source, and then we have three sections of this circuit connected in parallel. As you can see right here, the section 1 is this section right here, which is connected in parallel with section 2, which is connected in parallel with section 3. In other words, these three sections they have they have a common point of connection right here on top and in the bottom. Let's see if so right here is a connection, and right here is another connection. Remember, this is a wire basically, a connector right here, and a connector right here. And these three sections, section 3, section 2, and section 1, they're all connected to the same common points. So therefore, they are connected in parallel. However, branch 3 only has one resistor. Branch 2 has two resistors, even though branch 2 and branch 3 are connected in parallel. Within branch 2, you have two resistors connected in series. So determine what is the equivalent resistor for this string right here. It will be this resistor plus this resistor. So the sum of all the series resistor is the equivalent, the total resistance for this branch. In branch 1, we have three different resistors, but they're all connected in series. 1, 2, and 3. So we can replace this branch by one branch that has only one resistor, which will be the sum of all three of these series connected components. Another example here, well, the previous example is for serial connected circuits, series and parallel circuits. Okay, so we have branches that are connected in parallel, and within each branch we have components that are connected in series. On this one right here, we have three components, 1, 2, and 3, and these three components are connected in series. So if we follow this loop, as you can see, they are all one after another one, so they are connected in series. However, component number 1 is composed of two resistors, this resistor right here and this resistor right here, that form a bank of parallel components. These two components are connected in parallel, but the whole thing is connected in series with 3 and section 2. So section 2 is also a bank of two resistors connected in parallel. All right. So this circuit is a combination of series and parallel components. We have three major components connected in series, but within these two components we have parallel connections. Okay, here is an example. In this example, to find the total resistance for a series parallel circuit, we're going to add all the resistance that are in series, and then we're going to combine all the resistance that are in parallel. If we take a look at this, all right, so let's see. This resistor right here, R1 and R2, are connected in series. So to calculate the total resistance for these two, all we have to do is add R1 plus R2 because they're connected in series. R3 and R4 right here, these two components are connected through A and B, so they are connected in parallel. So we need to find the equivalent resistance for this parallel connection and the total resistance of these two series resistors. Once we find this and this, then we will have one connected with the other one in series. All right, and let me show you exactly what I'm talking about on the in here. Okay, for that circuit, all right, as you can see right here, we had R1, R2, R3, and R4. Okay, so R3 and R4 are connected in parallel, and R1 and R2 are connected in series. So we can reduce these two resistors into one by adding R1 plus R2. And that would be 0.5 plus 0.5, that will give you, this resistor is the same as these two combined right here. That would be 1 kilo ohm, okay? Half plus half will be 1, so it's 1 kilo ohm. R3 and R4 are connected in parallel. So we're going to find the equivalent resistor for these two, which, as we learned in chapter 5, to find the equivalent resistance of two resistors connected in parallel, you multiply R3 times R4 and then divide by the sum of both of them. So R3 times R4 divided by R3 plus R4. Okay? And then they both are 1 kilo ohm. So 1 times 1 equals 1, and 1 plus 1 equals 2. So this is 1/2, which is 0.5 kilo ohms. So these two can be replaced by one resistor that is 0.5 kilo ohms. Okay, and that would be the equivalent resistor for these two. Okay, remember, when you connect, when you have a parallel connection, the equivalent resistor must be less than the smallest one of these two. So these two are 1, so the resistance have to be less than 1, which is 0.5, which is okay. Now, this can also be calculated by doing 1 over R3 plus 1 over R4. Okay, when you solve the algebra for this, you're gonna end up with that, and that's where this formula is coming from. Okay, this is what you use when you have only two resistors. If you have more than two, then you might want to do it this way. Okay, but if it's only two, this is the formula you're gonna use. So these two resistors right here, 3 and 4, can be replaced by this one right here, and 1 and 2 can be replaced by that one. So at this point, we have 1 and 2 resistors in parallel. In series. Okay, so they're in series because they are in the same branch, right? The same path. Okay, so because they're in series, all we need to do is add this one plus that one, and we can replace the whole thing with one single resistor, right? So if this is 1 kilo ohm and this is 0.5 kilo ohm, so we can add 1 plus 0.5, and that gives you 1.5 kilo ohms. So this whole resistor is equivalent to this resistor right here. This circuit is equivalent to this one right here. And the voltage doesn't change, of course. All right. Now, if we need to find the current on this resistor, okay, we can find the current by doing the current equals the voltage divided by the resistor, right? So that would be the total voltage here is 1.5 volts, and the total resistance is 1.5 ohms. So this would be 1 amp. Okay, that would be the current that is flowing through this circuit, the total current. Okay. Of course, if we need to calculate this right here, remember, this is the total current, and this current must be split between this, because this is a node right here. So the total current comes in, and then it gets split this way and this way. Okay, and it will be proportional to the amount of the resistors. In this case, basically, if this is one amp, it will be 0.5 here and 0.5 there, because both of the resistors are the same. All right, so let's continue. In here, and this is the this part of the slides are just the same calculations I just did on paper. Okay, this is another example. All right, this example is for figure 6.3a, and we have the same situation here, a similar situation, right? So we have this branch is connected in parallel with this other branch right here. Now remember that this right here is one connection, right? That right there will be one point of connection, and this will be the other point of connection. So as you can see, this branch, and this branch, they both are connected through the same point, so they are connected in parallel. However, branch 1 has two resistors that are connected in series. So in this case, we need to add the two resistors in series first, and that will lead us to a branch with one single resistor, and then we have two resistors in parallel. All right, so let's see on this example. Okay, so this is the same circuit. All right, so we have a voltage source of 12 volts. We have a resistor of 8 ohms and a resistor of 4 ohms. They're connected in series, and this branch is connected in parallel with this other branch right here, okay, which has a resistor of 6 ohms. So the first step to solve this problem would be to find the total resistance on this branch. Since we have two resistors in parallel in series, so we need to add R1 plus R2, and that will be 8 plus 4 that equals 12 ohms. So this branch is the same as this one with 12 ohms. This one is only a single resistor, so we keep that for now. And now we have these two resistors connected in parallel. Right? So if they're connected in parallel, we're going to multiply this one times that one and then divide it by the sum of both of them, like we did here. Right? So 12 times 6 divided by 12 plus 6 equals 4 ohms. So this whole thing, this whole circuit right here has an equivalent resistance of 4 ohms. Okay? So now once we have the equivalent resistance and we have the total voltage applied to the circuit, we can just divide the voltage divided by the resistance, and that will give you the current that flows into the circuit, and that will be the total current. All right, so we have 3 ohms. 12 divided by 4 equals 3 amps. I'm sorry. All right. Now in here we have 3 amps coming in because that's the total current, but when it gets to this point of connection right here, it splits between this branch and this other branch. Okay, and the amount of current that's going to go through these branches, it will depend on the resistors on each branch, right? So now these two are connected in parallel, right? So that means that the voltage here from this point to this point, all right, is the same from this point to this point or this point to this point because they're connected in parallel. Remember from chapter 5 that the voltage across parallel connection is the same for every single branch. So that would be 12 volts going through this branch, 12 volts going through this branch. If we know the voltage and we know the resistance, we can find the current that goes in this branch. Would be 12 divided by 12 equals 1. So 1 amp goes through this branch, and then 12 divided by 6 equals 2. So 2 amps go through this branch. So the current here is 1, the current here is 2, which if we add them together, we get the total current of 3 amps that we have previously calculated here, right? So the total current is 3 amps, and this one gets split like this. It goes 1 amp here, and 2 amps go this way. So now, if we need to calculate the voltage across each one of these resistors, well, once we know the current, all we have to do is multiply the current times the resistance. We already know from here that the current that goes into this branch is 1 amp. All right? I1 equals 1 amp. So 1 amp times, and remember that because these two resistors are in series, so they have the same current. The same 1 amp goes through this branch, right? So 1 amp times 4 ohms, that gives you 4 volts. And 1 amp times 8 ohms, that gives you 8 volts. For the current 2, this one right here, we determined already that it was 2 amps. Okay? From here, remember, you have a total of 3, and then 1 goes this way, so 2 must go in this direction right here. So we have 2 amps going through this branch, and we have 6 ohms resistor. So you multiply 2 times 6, and that gives you 12 volts. As you can see, this right here, 12 volts, is the same as the source because they're connected in parallel. So the voltage on each branch is the same when the connection is in parallel. All right. So you have 12 volts here, and this branch, the voltage across this branch from here to here, it must be 12, just like the source, right? So you have 12 volts going through this branch, which you dropped 8 across this resistor and 4 across this other resistor. 8 plus 4 equals 12. All right, so that was the resistance string in parallel. This is one string right here, and that's another one, and they both connected in parallel. So when you have series circuit, just remember that the current is the same. If you have a branch that has multiple components connected in series, just remember that the current on every single string is the same for all components. And the voltage across each one of the components, in this case, it will be each one of the resistors will be the current times that resistor. Just the same way that we calculated in here. Remember, we have 1 amp going here, so it's going to be the current 1 amp times this resistor gives you the voltage, and then 1 amp times this resistor gives you the voltage for this one right here. In here we have 2 amps current, so if we multiply the current times the resistance, that will give you the voltage. Okay, and the voltage in series components, the total voltage must be equals to the sum of the voltage on all the components. Okay, so if we say that in this case, for example, that this branch right here has 12 voltage, that's the total voltage. The total voltage must be equals to the sum of all the voltage in series. So the voltage across this resistor plus the voltage across this other resistor must add up to the total voltage applied, which is 12 volts. 4 plus 8 equals 12. Okay, so these are some of the characteristics for series circuit. Remember, in series components in a circuit, the current will be the same for all components. The voltage across each one of the resistors in series is the current times the specific resistance, and the total voltage on the series circuit, it must equals to the sum of all the voltages across all the components connected in series, of course. Now, when the connection is in parallel, there's some difference here. Okay, so if you have connected components connected in parallel, the voltage is the same across all branches. Okay, let me go back to this one. This branch and this branch are connected in parallel, so the voltage across this branch must be equals to the voltage across this branch. Okay, so these 12 volts are applied here to this point, and remember that this point is a common point for both branches. Okay, so this point right here and this point, they have a 12 volts across. So 12 volts go here, and 12 volts go on the other branch as well, because they're connected in parallel. Just like the voltage, the total voltage, okay, just like the total voltage on the series connected circuit must be equals to the sum of all the voltages across every component. When the connection is in parallel, is the total current the one that must equals the sum of all the currents. Okay, the total current is equals to the sum of all the branch currents. Okay, and the current in each branch, it is the voltage divided by the resistance for that branch. We calculated here, right? this connector right here, this connection is a series connector, right? Connection. So the sum of the voltage must be equals to the total voltage. This branch and branch 1 and branch 2 are connected in parallel. So the sum of the branch current must be equals to the total current, okay? So you add the voltages to match the total voltage in series connections. You add the branch currents to match the total current in parallel connections. Okay. Here is another example in which we can say that the voltage is the same in all of these branches. All right, let's see. This branch and this branch are connected in parallel with this branch right here. This is considered one branch, all right? Because all these are connected in series, but they're all connected to this point right here, which is the common point for all three branches, all right? If you can see, this is just like a wire that goes in there, so this could be like this, right? Or like this. Right? So you can have three branches connected. So this distance right here doesn't mean anything. This is just the same point of connection, right? So all three branches are connected in parallel. So branch 1, branch 2, and branch 3. However, if you look at branch 1 only has one resistor. Branch 2 has two resistors connected in series. So to find the total resistance on this branch, we can just add this resistor plus this other resistor to give you the total resistance on this one, right? Now on this last branch, this branch right here, this one has three resistors connected in series, all right? You have that one and that one and this one. So this series connection can be reduced to one single resistor, which will be the sum of all three resistors, okay? Because they're connected in series, we can just add them all up. And then we can reduce this circuit to three single branches with a connection that is in parallel. All right? Here we have another example. Okay, of connections that are in, there is a parallel connection here and another resistor that is in series with this bank. Remember, parallel connections are called banks. All right, so let's see how we're doing with time. All right, so let's do this problem. As you can see right here in this figure, R2 and R3, which are this resistor right here, this one and that one, they're connected in parallel, right? This is a parallel connection right here. And this bank is connected in series with this resistor right here, okay? So the first step will be to solve this bank in order to find the equivalent resistor, and then we can add this resistor to that to find the total resistance of the circuit. We can apply Ohm's law to find the voltage and the current. So once we find the total resistance, we can determine the current, right? So we have 24 volts applied in here. So we have, this is a 10 ohm resistor and this is a 10 ohm resistor. So if we multiply 10 times 10 equals 100 divided by 10 plus 10 equals 20, so all this can be replaced by one single resistance that is 5 ohms. Okay, so 5 ohm plus 1 ohm here, that would make it 6 ohms, and then divide 24 divided by 6, that will give you 4 amps current. So now we know that the current in the circuit will be 4 amps. That will be the total current. However, this current will go through this bank and through this resistor right here. It will be the same current going through it. However, when it gets to this point right here, these 4 amps are going to be split this way and this way, right? So because the resistors are basically, let's see, the same, right? This is 10 resistor and 10 ohms, and this is 10 ohms, so this will be evenly distributed. The 4 amps will go 2 amps this way and 2 amps this way. And then when they get to this point, they combine again, and then 4 amps go out this way. Okay, and there will be the same 4 amps going through this resistor, because remember, the resistance is the same. The voltage will be split, because remember, when you have series components, the voltage across all, the sum of the voltages across all the components must be the total voltage, right? So if we already know that the current is 4 amps, so we can calculate the voltage across this resistor, right? So 4 amps times the resistance of 1 ohms, that will give you 4 times 1 equals 4, so that would be 4 volts is the voltage across this resistor right here. Right? So we have 4 volts across this one, and the total is 24 volts. That means that there is a difference of 20 volts that have to be dropped in this bank, right? So from here to here, there is a voltage drop of 20 volts, because there's 4 here, so 4 plus 20 equals 24. And here it is. How do we calculate this? Remember, the voltage in parallel connections is the same, right? In every single branch is the same. So if I know that I have 2 amps going this way in current, and the resistor here is 10 ohms, so 2 times 10 equals 20. So there is voltage drop across this resistor of 20 volts, and because this one is connected in parallel with this one, so 20 volts must be dropped over this resistor as well. Okay, remember that parallel connection have the same voltage on every single branch. So you got 20 volts through this bank and 4 volts through this resistor. There is a total of 24 volts, which is the total voltage. Okay, and here we go. See, this is the same operations that we just talked about. The resistor is the total voltage divided by the current is 24 divided by 4, and the total resistance will be 6 ohms, right? That is what we determined here. You have 10 ohms and 10 ohms, so the total resistance for this would have to be less than 10, which is 5, plus 1, that would be 6. Ohms. All right, so now this circuit is going to be a little bit more, it requires a little more analysis, so I'm going to stop right now, and I'm going to pick back up section 6.4 on the second part of this lecture. Okay, so until then, thank you for your attention, and I will be analyzing the rest of this chapter on the second part of the lecture. Okay, thank you so much.